So in chapter 7, section 2, you learned that if a quadrilateral was a parallelogram, you learned all these different things about angles that would be congruent, sides, whatever, right? Well, in this chapter 7, section 3, what you're going to do is you're going to have a quadrilateral that you don't know is a parallelogram, but you're going to use theorems to prove that the quadrilateral is a parallelogram. So the first one starts out parallelogram, opposite sides, converse. And if you remember, you had a parallelogram, opposite sides theorem in the last one. In 7.2, we taught you that if the opposite sides, if the shape was a parallelogram, then the opposite sides would be congruent. Well, here, what they're saying is that if both pairs, it has to be both pairs, if both pairs of opposite sides of a quadrilateral are congruent, so notice that this is the hypothesis in the converse, okay? Then the conclusion is that the quadrilateral must be a parallelogram. So again, in the original theorem, the hypothesis was that it was a parallelogram, and the conclusion was that the opposite sides are equal. Here, the hypothesis is that both pairs of opposite sides are equal, and therefore the shape must be a parallelogram. So again, if you note that the opposite sides are congruent to each other, as they are here, then quadrilateral ABCD is a parallelogram. So we're going to go to the next one, opposite angles converse. Again, if you know the shape is a parallelogram, you know the opposite angles are congruent. In this converse, what they're saying is if both pairs of opposite angles of a quadrilateral are congruent, then the conclusion is the quadrilateral must be a parallelogram. So once again here, you're noticing your opposite angles, B and D are congruent, A and C are congruent, and therefore ABCD must be a parallelogram. Here we have the opposite sides parallel and congruent theorem. So again, this one says that if you have, this one's a little bit different. Notice it's not a converse. This is a new theorem. This theorem says that if you have one pair of opposite sides congruent and parallel, then the quadrilateral is a parallelogram. So this is the one of the few where you don't have to prove both pairs, okay? So notice here it says, basically, if I have, notice these opposites, I have the BC and AD are congruent, and BC is parallel to AD. And so that's enough to prove that the quadrilateral is a parallelogram. So it's if BC is parallel to DA and, okay, BC is congruent to DA, then the quadrilateral is a parallelogram, okay? And again, one is your hypothesis here, and this is your conclusion. So this is the only time when one pair is enough. Okay, and then the last one here, parallelogram, diagonals, converse. And again, remember the original theorem was that if you knew something was a parallelogram, then you knew the diagonals bisected each other. Here, it says if the diagonals of a quadrilateral bisect each other, and diagonals meaning both of them, then the quadrilateral is a parallelogram. So again, your conclusion is always that it's a parallelogram. So again here, you might not be told this is a parallelogram, but you notice that here's the point of intersection, and let's just call this M. BM is equal to MD, and AM is equal to MC, and you're like, oh, M is the midpoint, so these two, of both of the segments, so these two diagonals bisect each other, and therefore ABCD is a parallelogram. So how do you prove a quadrilateral is a parallelogram? Well, all of the theorems I just talked about. Number one, the opposite sides, the parallelogram opposite sides converse. This says show that both pairs of opposite sides are parallel. The second one, show that both pairs of opposite sides are congruent. The third one, show that one pair of sides are parallel and congruent. So here's the only time when you're showing that one pair is parallel and congruent. It has to be both things. Again, here's another, both pairs of opposite angles are congruent and that the diagonals bisect each other. So really, 1, 2, 4, and 5 all come from the converses from the theorems you learned in 7.2. The only unique one is 3. That's a new one. So ways to prove a quadrilateral is a parallelogram. Well, again, by definition, right? This one we didn't really talk much about. It wasn't in the slides, but if you can show that both pairs of opposite sides are parallel, that just is the definition of a parallelogram. And so, yes, you would have that. Number 2, show both pairs of opposite sides are congruent. That's a theorem. Now, this theorem here, 7.7, don't worry about the number in which it shows up, so don't worry about that. Show both pairs of opposite angles are congruent. So both pairs. Again, don't worry about the number. Again, this is just a summary. One pair of opposite sides are congruent and parallel. Okay? And then the diagonals bisect each other. So now let's put into practice all those things that we've been talking about, because it's been a little bit repetitive. Now I'm just going to put it into practice. So, for example, state the principal definition or theorem that enables you to deduce from the given information that the quadrilateral is a parallelogram. So in 1, it says segment BE is congruent to ED and CE is congruent to EA. So I know that this is the theorem, a converse that we just learned, right? And it's the diagonals converse theorem. And I should probably do like parallelogram diagonals converse theorem. Okay, and again it says that if the diagonals bisect, if both pairs of diagonals bisect each other, then the shape is a parallelogram. All right, let's go to the next one. It says, let me erase this red one. Well, let me just erase that. Okay, so the next one says angle BAD, so BAD, this big angle here, okay, is congruent to DCB, this big angle here, and angle ADC, this angle, is congruent to angle CBA, which is this angle. And so notice both pairs of opposite angles are congruent, and therefore it's a parallelogram. So it's the parallelogram opposite angles converse theorem. Okay, which says if the opposite angles, both pairs, are congruent, then the parallelogram, then the quadrilateral must be a parallelogram. Then we go to number 3. Number 3 says, let me erase the 2, right? Number 3 says BC is parallel to AD. BC is parallel to AD, and AB is parallel to DC. And so notice that we have 2 pairs of opposite sides which are parallel to each other. So this is definition of a parallelogram, okay? So the definition, if I can prove that these 2 sides are parallel and these 2 sides are parallel, then I know the shape is a parallelogram just because it meets the definition of a parallelogram, okay? So it's just a definition, not a theorem. I keep going. Let me go to number 3. So number 3 says, or number 4 rather. Number 4 says BC is equal to AD. This side is equal to this side, and AB is congruent to AD. So notice that my opposite sides are congruent. So this is parallelogram, opposite side converse theorem. And it's a converse because we know we learned about the original theorem yesterday. The original theorem proves proves that the opposite sides are equal. The converse proves that it's a parallelogram. And so the last one we're going to do is number 5. Number 5 goes into, this is the one unique one that we learned here. Number 5 says that BC is parallel to AD, and it says that BC is equal to AD. So we know that if we have a side that is one pair of sides that is parallel and congruent, that the shape must be a parallelogram. And that's called opposite side parallel and congruent theorem. Notice it's not a converse because this is not something we learned about before in the previous sections, or there's no theorem that started this. And so these are, this again, a converse theorem, a definition, another converse theorem, and then a regular theorem. So there's a lot of information here that you're going to have to memorize. All right, so now how do we apply it, right? We know what's parallel, we know what's not, we know if it's a parallelogram. How do we apply that in actually solving a problem? So the first question we're going to see here is it asks us, for what values of x and y is quadrilateral PQRS a parallelogram? Well, remember that it's a parallelogram if both pairs of opposite sides are congruent. So in other words, if y equals x plus 7 and, let me do it side by side, and if x plus 9 equals 2x minus 1, then this is going to work. So obviously, I really can't work on this one too much because notice I have one equation in two variables, and I can't really use that to solve. But I can solve the other one because notice that this equation here is all x's. So I'm going to solve for x. I'm going to subtract 2x from both sides, and then I'm going to subtract 9 from both sides. Last step, I'm going to divide by -1, and I'm going to get x is 10. So if x is 10, my PQ, right, is going to be congruent to SR. And so again, let's just try it. 10 plus 9 is 19, and 2 times 10 minus 1 is also 19. So notice that's a good thing. So x is 10 is good. Now, since I know x is 10, I can come over here and plug 10 in for x, and I can find my missing value. So y is 17. So if x equals 10 and y equals 17, right, then PQRS will be a parallelogram, okay? And so that's how you do that. Okay, another one. For what values of x and y is quadrilateral ABCD a parallelogram? Notice x and y are now talking about angles. Well, remember, if my opposite angles are congruent, then my shape is a parallelogram. So let's find the values that'll make that happen. 3x minus 32 has to equal 2x, and 4y has to equal y plus 87. Now this one's really easy because notice the equation that I set up for angle A and angle C, notice that it just has x's in it. And again, remember that for this to happen, right, I mean, I could kind of start like that. Angle A has to equal angle C, right? And angle B has to equal angle D. Okay, because again, both pairs of opposite angles have to be congruent. Remember that converse theorem. So anyway, now I'm just going to do the math. So I'm going to subtract 3x from both sides, and I'm going to get minus 32 equals minus x, which means x is 32. That's one value. And then I'm going to subtract y from both sides, and I'm going to get 3y equals 87. And then I'm going to divide both sides by 3, and I'm going to get y equals 29. And so if x is 32 and y is 29, so if this happens, then ABCD will be a parallelogram. Okay, so those are my values that are going to make it happen. Your theorem says that if two lines are parallel and they're crossed by a transversal, the alternate interior angles are congruent. Okay, and then the last one, they want me to write a proof. And so they want me to write a 2-column proof. Again, I'm not even sure what they want me to prove yet, but let me at least get this started. My statements, my reasons. Whoops, it's kind of sloppy, but whatever. Okay, step 1. I know step 1 is going to involve some givens here. So ADB is congruent to angle CBD, and angle ABD is congruent to angle CDB. Okay, so look at that first, right? So ADB, this little angle right here, is congruent to CBD, this angle here in purple. And then angle ABD, this one here in green, is congruent to CBD. So I'm already kind of seeing that if those angles are congruent, then I know that the lines are going to be parallel to each other. So, but anyway, let's just start here. I know that this is my given. Okay? So, let me kind of erase this and we'll do it now. Okay. So, I'm going to start with one of those at a time, right? I know that if, let's start with this angle here, okay? I know that if those two angles are congruent, and I have this transversal, if those two angles are congruent, then I know that this line and this line must be parallel to each other, okay? Because that's the alternate interiors converse theorem. So I know that AD is parallel to BC, and I know it because it's the alternate interior converse theorem. So if you remember, you originally learned about alternate interiors theorem or angles theorem, and it said that if you had two parallel lines and they were crossed by a transversal, the alternate interior angles would be congruent. Then we learned the converse to that, which said if two alternate interior angles are congruent, then the lines must be parallel. And so it allows me to conclude, okay, alternate interior converse theorem or alternate interior angles converse theorem allows me to prove that the two lines are parallel. Okay, then I'm going to go to number 3 and I'm going to prove the same thing with the other two parallel lines. I know that AB is going to be parallel to DC because the alternate interior angles are congruent here as well. So AB has to be parallel to, DC? To DC. And again, it's the same thing. It's the alternate interior angles converse theorem, which says that if the alternate interior angles are congruent, then the lines must be parallel. So now that I've proven that this quadrilateral has two pairs of parallel sides, so basically this is what I've come to prove, right, is that that BC is parallel to AD and that AB is parallel to the other one. And so now I can prove that parallelogram ABCD is a parallelogram. And the reason that I can prove it is because of the definition of a parallelogram. Okay, remember the definition says that if a shape has two pairs of parallel sides, or if a quadrilateral has two pairs of parallel sides, then it's a parallelogram. So the definition is the one that gives me this final answer. And that's it. So again, you kind of got to go back to, and it's something that it's a good thing to review back to your chapter. Okay, review chapter on parallel lines and transversals. Okay. on parallel lines and transversals. Because every time you draw a diagonal through a quadrilateral, you're going to have a potential transversal, okay? And so this scenario is going to happen a lot.